Let's start from the beginning. The platform engineering experience of installing AI Runway. I apply a single YAML file to my cluster, and that installs both the controller and the dashboard. That's the core platform up and running. Next, I need to connect a runtime. I'll apply the KAITO framework adapter. This is a small YAML file that tells AI Runway how to talk to KAITO, what engines it supports, and what capabilities it has. Think of it as a plug-in registration. It's how the platform stays extensible without any runtime-specific code baked into the core. Now let's switch to the user experience. This is the model catalog, the first thing your data scientists and developers see. Think of it as your app store for AI models. We have a curated set of popular models, Qwen, Phi, DeepSeek, Llama, each with a quick summary, how big it is, what engines it supports, and what it's good at, chat, text generation, multimodal, and so on. But the real magic is this GPU fit indicator on every card. It tells you instantly whether a model will actually run on your cluster. No guesswork, no trial and error. Before we deploy, let's connect our HuggingFace account, because some of the most popular models are gated, meaning you need to authorize access to use them. Over in Settings and Integrations, I'll click Connecting with HuggingFace. Now, normally with other frameworks, this is painful. You have to go to HuggingFace, generate a personal access token, copy it, create a Kubernetes secret, and so on. Here, it's just a standard OAuth flow, like logging in with Google. One click, authorize, and done. Now, two things get done here. I can now search and deploy gated models as well, which is great, and the token gets stored as a Kubernetes secret automatically so that the cluster can pull model weights during deployment. One login and it just works. Before we deploy something, let's also take a quick look at the Runtime tab, where you see the inference frameworks that run your models under the hood. AI Runway supports multiple runtimes, and it's entirely extensible, so you can choose a different runtime when you want. You're never locked in. Let's highlight two here. KAITO, the Kubernetes AI toolchain operator, is the most flexible. It supports both vLLM and llama CPP, which means it can run models on both GPUs and CPUs. It's the only runtime here that gives you CPU inference, which is great for smaller models where you don't want to spin up expensive GPU nodes, like in development and testing, and it runs well on the edge. And the second is NVIDIA Dynamo. It's the high-performance choice. It supports vLLM, SGLang, and TensorRT-LLM. What makes it special is disaggregated serving. It can separate, prefill, and decode into independent worker flows. Plus, it has KV cache-aware routing for smarter request distribution. It also has an AI configurator that can automatically optimize your deployment for things such as tensor parallelism, batch size, and others, all tuned for your specific hardware. The Runtime tab lets you select either of these or any other runtimes you want to use. Now that we're connected, let me show you the HuggingFace tab. I can search the entire hub from right here, and because we're logged in, the gated models show up too. Look at this large model. See the red bar? It says won't fit. It needs more VRAM than the GPUs currently running in our cluster. You can see exactly how much more you'd need. No surprises, no failed deployments. Now compare it to this smaller model, the green bar. Perfect fit, plenty of headroom. You know even before you click deploy that this one's good to go. Let's start with a simple deployment. I'll pick a compact model. This is a quantized version. Think of it like a compressed file. It's not as accurate as the full precision model, but because it's so small, it can run on CPUs. I select KAITO as the runtime. It's the one that supports CPU inference. I switch the compute type to CPU, pick the gguf quantized file, and that's it. This is great for development, testing, or scenarios where GPU capacity is expensive or constrained. The model runs on standard CPU nodes already in your cluster. Quick, cheap, and no GPU is needed. Now here we've sped up the deployment slightly, but when our deployment is running and we have our gateway endpoint ready, we can use the chat app to see if the endpoint is responding correctly. So we type out hello world, and there we have it, up and running properly. Straightforward whether you're a Kubernetes expert or not. Now let's go to the other extreme. Let's go to the HuggingFace gallery and search for DeepSeek R1. 671 billion parameters. This is not going to fit on our single node, which has 8 H100s. So I then go into deploy and I select Dynamo as the runtime. And this is a good moment to talk about why. For large models with high traffic, runtimes like Dynamo and llm-d really shine because they support disaggregated serving. Now, what does that mean? Normally, inference has two phases, prefill and decode, and they run together on the same resources, which is fine for small workloads. But when traffic gets heavy or the model is very large, it becomes a bottleneck because you can't optimize or scale each phase independently. Disaggregated serving separates prefill and decode into different resources, so each phase can be independently scaled and optimized. This improves GPU utilization, throughput, latency, and ultimately cost. For this demo, we'll use aggregated mode, but for production workloads with heavy traffic, disaggregated serving is where these runtimes really differentiate themselves. Now, before I configure all of this manually, watch this. I'll click Optimize and let the AI configurator do its thing. It analyzes the model against our available GPUs and comes back with a full recommendation. Tensor parallelism, batch size, context length, engine selection, all optimized. I can see the estimated throughput, P50 and P99 latency, and if I hit Apply Configuration, the entire form fills in automatically. In this demo, however, we won't do that, and instead add our own basic configuration. We'll deploy into the default namespace and continue down the options. As you can see here, because this model is so large and one node was insufficient, it is recommending 3 nodes that will have 24 GPUs in total. And because the autoscaler is enabled on this cluster, when we deploy, we will eventually receive the extra nodes that we need. Now here's where storage volumes come in. I'm attaching a persistent volume backed by Azure Managed Lustre. This is a high-performance shared file system. The model weights get cached here, so on restarts or scale-out, the new nodes don't have to re-download hundreds of gigabytes. It's read-write many, so all nodes can access it simultaneously. Let's just configure this. And here use the one I've already created. You can also see the cost estimate updating in real time. We have a good idea exactly what this deployment costs per hour and per month on Azure. This value represents the eventual 3 nodes with 24 H100s and will vary depending on cloud provider. Right now, our cluster only has a single H100 node, 8 GPUs. But DeepSeek R1 needs 24 GPUs across 3 nodes. So what happens when I hit deploy? We'll skip ahead here since autoscaling takes a few minutes, but once those nodes come online, the deployment rolls out across all 3 nodes and goes to running. Now that DeepSeek R1 is running, let's use it. In the deployment page, we can see our storage and the mounted disk, and you can see the gateway endpoint. AI Runway integrates with the Gateway API Inference extension using Istio in this case. This gives us a single stable endpoint for all our models. There's also a ready-to-use curl command. It's a standard OpenAI compatible API. Any tool or SDK that speaks OpenAI can talk to your models without modification. What's really powerful here is the gateway does body-based routing, and it works across runtimes. So if you have models running on KAITO, Dynamo, and llm-d, all behind a single endpoint, the request gets routed to the right model based on the model field in the JSON body. 10 different runtimes, 100 models, 1 URL. That's the power of this abstraction. I'll hit Open in INA to open up a simple chat application that connects directly through the gateway. It pre-fills the connection details, so I'm chatting with the DeepSeek R1 in one click. Any application can do this, and INA is just an example. So what have we seen? AI Runway gives you a unified, provider-agnostic way to deploy ML models on Kubernetes. Your platform engineering team controls which runtimes are installed, just like you want them to. Your users browse a catalog, see instantly whether a model fits their hardware, pick a runtime, and configure with a few clicks. Or they let the AI configurator do it for them. From a tiny, quantized model on the CPU to a 671 billion parameter model auto-scaling across H100 nodes with Azure Luster. You get disaggregated serving for production workloads, a unified gateway endpoint that works across all runtimes, cost visibility, and it's fully extensible. One platform from CPU to multi-node GPU.